In this video, we're going to give a brief introduction to the idea of limits. We'll start with the definition. The limit as x approaches a for the function f of x is written with this notation. So it's the limit as x approaches a of this function f of x is equal to L. We're taking L to be the value of the limit. So what this is saying is that as the x value gets closer or approaches the value of a, whatever it might be, whether it's 2 or 3 or 4 or -5, right? As x gets close to it, use this arrow to represent that, then what happens to the y value or the function value, y? Does it approach some number, right? As x gets closer to a certain number that we're paying attention to, does the y approach a certain number? If so, it's called the limit, and you can also use that arrow notation for the y as well. So I thought I'd just use this as a quick example. I think the graph is the easiest way to see this happening. So this graph is a parabola, x squared minus 3, and I've put a little hole here, okay, which in all honesty, we could look at this place on the graph with or without this hole. We'll kind of mention that in a second. So if we wanted to find the limit as x approaches 2, we could write f of x to represent this function, or we could just put x squared minus 3. Okay, so as x gets closer and closer to 2, right, here x is 1. We could even label these, right? This is 1, -2. This is 0, 1. This is what, 1.5, maybe -1. Okay, I'm kind of guesstimating. We could plug it in, but I won't do that on the spot because I might mess it up. All right, but as the x value gets closer and closer to the value of 2, right here, the y value is getting closer and closer to the value that we see in this point, to the point 2, 1. Right? And so this is actually from the left, right, as the x value is getting bigger, approaching 2. But we really want to talk about it from both directions. So as x is also coming from, say, 3 to 2.5 to 2.25 to 2.1 down to 2, the y value is also approaching 1, right? We're kind of watching it approach on both sides. So that means that the limit is 1. And so this idea, the limit, is the idea of, is exactly that, right? As x gets close to a certain number, what's happening to the value of the function? Does it approach a certain number, or does it go off to infinity, or does it do all kinds of crazy things? It could bounce around, lots of things, right? But if it approaches the same number on both sides, then we say that the limit has a value, and we list that value. In this case, that would be the value of 1. Okay, there are a few things that I chose to type out here. So it says, the first one is, for the limit to exist, the y value should approach the same number, L, whether x approaches from the left or from the right. We kind of just said that, right? So if it doesn't approach the same number from the left and from the right, then we would say that the limit does not exist. But if they do indeed approach the same number, like these both approached 1, then that's the value for the limit. As we can also see in this example, the limit may still exist even if the function cannot be evaluated at a, right? In that picture we just drew, we didn't have a value there. We had an open hole. So it really doesn't matter what happens at this, for this above, our example was when the x value was 2, right? Doesn't necessarily matter what's happening right at 2. The limit really describes what's happening around 2. Is the y value getting close to one number, right? It doesn't necessarily have to be that the function has a point there, although it definitely could. It could be a point, it could be a hole, right? Or it could kind of approach infinity. We'll talk about that in a minute. Okay, if the limit does not exist, I guess what's usually written is D and E, right? Does not exist. Okay, so let me give you a couple of examples. Well, actually, we're going to add to this first before we do that. So we have something that's called a one-sided limit, and this kind of deals with that idea of approaching from the right or approaching from the left. And when we say the left, we mean numbers that are smaller than our number of interest, x value of interest, getting closer, getting larger up to that value. And then from the right is always larger, getting smaller as we get close to that value. Okay, so from the right, we denote that with a little plus. It's like a superscript, kind of like an exponent, but not. And then from the left, we use a negative, same thing, right? Like a superscript, sort of. I thought we could look at the two examples we just talked about in the last video that were described as piecewise functions, right? So one of them we looked at was the absolute value. So this is a good example, right? So if we look at the limit of the absolute value of x as x approaches 0 from the left, that would be coming in from this way. What is happening to the y value? Is it approaching a certain number? Yeah, absolutely. It's approaching this point right here in the middle, right? So the y value is going down as the x value is getting closer to 0. The y value is getting closer to 0 as well. Okay, what about the limit at x approaches 0 from the right? Would be coming from this direction. What's happening to the y value? It's also going down, getting close to 0. Okay, if the limit from the left and the limit from the right are the same, then we can say kind of that standard limit that's not one-sided, right? It exists because we're approaching the same number from both sides. And so in general, the limit as x approaches 0 is 0. Right? We have to have these two in order to get this value. Okay, let's try another example. For this one, I've got the piecewise function that we looked at last time. So this was the piecewise function where part of it was x squared, like a parabola, and the other part was the square root, right? And it sort of had this shape. So if we want to look at the limit of this function as x approaches 2 from the left, that means where values are smaller than 2 and getting closer and closer to 2, that's really going to be generated by the first piece, right? The x squared piece. So as we are coming from the left, getting closer and closer to 2, notice the y values are leading up to this open hole that we've drawn. So the y values are getting closer and closer to what point would be right there, which has a y value of 4. Right? 2 squared is 4. Okay, and then the limit from the right, as x approaches 2, would be coming from values that are bigger than 2, getting smaller towards 2, which is going to come from the second piece. And so as we move along this curve, the y values are approaching the square root of 2, or we approximated that as 1.4. Okay, so what about the general limit? Not a one-sided, but just in general, as x gets close to 2, is the value of the function approaching one number? And the answer to that is no, right? On the right, it's approaching this number, and on the left, it's approaching this number. So it's not consistent right there at 2. And so this limit does not exist. This is one of those times when it does not approach the same value. Okay. One more thing here. Cover this up for the moment. So the limit of f as x approaches infinity, right? So let me just read what we have here. As x gets larger and larger, the value of the function f of x gets closer and closer to L. This limit follows closely to the idea of the horizontal asymptote. So at the ends of the graph, when x gets really large, right, and I used positive infinity here, but I could have used negative infinity just the same, right? So as x gets really, really large, think the ends of the graph on the far left and the far right, does the y value kind of level off like we've looked at in the past to some specific number? So it really is in line with that horizontal asymptote idea. So if it does level off at some specific number, whether it touches it or not, we would say that this was the limit, the value of the limit. Okay, kind of separate from that, but sort of similar idea where the role of x and y are swapped. We could get infinity as the value of a limit, right? So maybe the limit as x approaches a is infinity. So I'll just read what I have here. This expresses the way in which the limit does not exist. The function grows arbitrarily large. So as I get closer to this value, the y value just grows really fast, uncontrollably, right? And goes to infinity, or maybe it goes down to negative infinity as we get close to that x value. Rational functions make really good examples for this type of limit. So I wanted to show you a graph of a rational function, which we've taken a lot of time to talk about how to graph these, and just kind of throw in all the limits we've talked about so far into one example so you can kind of get a good big picture. All right, so we want to start with this function here. To be able to graph it, we've got a factor, right? So I did that for us. And then notice I have x minus 5 in the top and x minus 5 in the bottom, so I can cancel those out. Okay, I don't think I didn't write much else there. I just wrote a bunch of limits. Okay, so let's just talk about where the graph comes from one more time as a reminder, right? If I have space, maybe I'll try to squeeze it up here, right? So the vertical asymptote is we're going to cancel and reduce and then set the denominator equal to 0. So that's going to be x equals negative 5. So I already have this printed here, but we could draw in, right, that dotted line. Okay, the horizontal asymptote. We can either look here or in the reduced version. We look at the power of x in the top compared with the power of x in the bottom. Notice this time they're the same. Since they're the same, we want to take the coefficients out front. So there's a 1 over a 1. So the y values are going to approach 1. So we've drawn in this dotted line. Okay, and then we do have a hole. If I cancel, that's when I know I'm going to have a hole. So I canceled out x minus 5. If I set x minus 5 equal to 0, that tells me that the x value of the hole is going to be 5. And then if I plug 5 into the reduced function, so sorry, I was doing markers today. If I plug in 5, 5 minus 2 would be 3 over 5 plus 5 would be 10. So 3 over 10 would be like 0.3. So I have a hole at 5, comma 0.3. Okay, so now that we've got all of that, let's look at a few limits. The first one here we have is the limit as x approaches 5 from the left. So as I'm coming from the left towards 5, my y value is getting closer and closer to my hole, which has a y value of 0.3. How about the limit as x approaches 5 from the right? Same, I'm on the same curve, but now I'm coming in this way, and the y values are still going to get closer and closer to the y value I have of my hole. Since these are the same, the limit as x approaches 5 from both sides, they're both approaching 0.3. Let me just draw a line here. Whoops, because those kind of go together. All right. The next three we have, how about the limit as x approaches negative 5 from the left? So here's negative 5. As I approach that from the left, the y value is growing really rapidly and going up to positive infinity. You can write the plus or not write the plus. I'll go ahead and write it just to be clear. Okay, how about the limit as x approaches negative 5 from the right? So as I'm coming in from the right, the y value is shooting down to negative infinity. So the limit overall as x approaches negative 5, notice these do not match for sure. So this limit does not exist. Right? They don't both go to infinity, they don't both go to negative infinity, they're going in opposite directions and they're kind of blowing up. So they're not approaching a specific value. So this does not exist. Okay, what about the limit as f of x approaches positive infinity? So as x gets really, really large on the positive way on the right here, this is where that horizontal asymptote comes into play. So the y value is going to get closer and closer to the horizontal asymptote, which is at 1. Likewise, on the left, as x gets closer and closer to negative infinity, as we travel in this direction, the y value is going to get closer and closer to 1 from above. Since these are not really a specific number and they're kind of heading into opposite directions, we can't really combine them into one whole limit, right? That doesn't translate for this infinities. Okay, well, I hope I gave you a little bit of an idea of what a limit is, how we can use a graph to help us determine that value of the limit, and kind of looking at limits at infinity, what happens with those as well. So take some time to practice these, look at some other examples. Good luck. We'll see you in the next video.